Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to have Shuicheng here to present his work in unified dimensionality reduction. Shuicheng got his PhD in Beijing University at the year of 2004. Currently, he is a postdoc research fellow with Professor Tom Huang at the UIUC. His research areas span the general areas of computer vision, machine learning, and video event analysis. So, yeah. We're looking forward to your talk.
Thank you. It's really my honor to visit the lab at Microsoft Research. So today I would like to introduce my work on future dimensionality reduction. So basically, I try to provide a general framework that unifies most previous algorithms on dimensionality reduction. This unified framework will include a general formulation and a general solution. So finally, I will also introduce my latest work on how to rearrange the tensor structure to improve the tensor-based subspace learning. So why should we or why need we conduct dimensionality reduction? I think one reason is for data visualization. For human, we can only visualize the high-dimensional data in the 2D or 3D space. If we just randomly select 2 or 3 features and then visualize in the 2D or 3D space, mostly we can't observe any useful information. But if we conduct dimensionality reduction with spatial purpose, we may observe the explicit semantics in the low-dimensional feature space. For example, in this figure, the results are from the algorithm called Laplacian phases. We can see that the first 2 dimensions characterize the variations of poles and the expressions respectively. Another reason is for the speed requirement. For example, for the image search, if you compute the similarity of two images, the computational cost will be extremely higher, especially when the database is large. Finally, I think the dimensionality can improve the algorithm learnability. Due to the cost of dimensionality, a possible way to improve the algorithm learnability is to reduce the feature size or feature dimension. So I think it's useful for dimensionality reduction. So for dimensionality reduction, you can directly compute the low-dimensional feature space for the training samples only, such as the algorithm locally linear embedding. This algorithm computes the low-dimensional feature space for the training samples but preserve the local reconstruction relationship with training samples. Also, there are some algorithms such as the ISO map and the Laplacian eigenmaps also belong to this category. For the popular linear dimensionality reduction algorithm, such as the principal component analysis and the linear discriminant analysis, they find a projection matrix and project the high dimensional feature into a low feature dimension space. One is unsupervised while another is supervised. The principal component analysis algorithm try to find the projection directions with maximum variation and best at reconstruct the original data, while the linear discriminant analysis try to find the projections good at classification. And namely, they try to find the direction which maximize the interclass difference, at the same time minimize the interclass differences. So in the past few years, many algorithms have been proposed to solve the dimensionality reduction problem when the training sample are represented as tensors instead of vectors. For example, the algorithm multilinear discriminant analysis, it extends the original LDA to the case with tensor data, and the concurrent subspace algorithm try to extend the PCA to the case with tensor data. For the vector-based linear dimensionality reduction, it has only one projection matrix for dimensionality reduction. But for the tensor-based dimensionality reduction, there may be multiple projection matrices that will be used for the dimensionality reduction. For example, for the third order tensor D, we are projecting into the lower size tensor Z with a projection matrix U1, U2, and U3. So, motivated from different perspectives, a large family of algorithms has been proposed to provide different solutions to the dimensionality reduction problem. Some are from the statistics, such as the PCA and the LDA-related algorithm, and some are from the geometry series, such as the ISO map, LE, and the Laplacian eigenmap. Also, the dimensionality reduction problem has been studied in different data representation, from the original vector to the matrix and to the general tensor. So we have hundreds of algorithms for dimensionality reduction. The next question is that, could we provide a common perspective to understand all these algorithms, or is it possible to provide a unified formulation that is shared by all of them? Furthermore, it is possible for us to provide a general tool to guide developing new algorithms for dimensionality reduction. So on the one hand, could we unify the most previous algorithm? On the other hand, could we provide a general tool to guide developing new algorithms? In this talk, I try to give positive answers to these questions. That is, most previous algorithms for dimensionality reduction can be unified in the framework of graph embedding, along with its linearization, kernelization, and tensorization. Specifically, I will introduce three of my works. The first work is on the graph embedding and the extension. And the second work tries to give a general solution to the dimensionality reduction problem. Finally, I will try to study on how to rearrange the structure of a tensor to improve the performance of tensor-based subspace learning. Now, let's begin the first work on the graph embedding. For graph embedding, there are two graphs mostly. One is the intrinsic graph. Another is a penalty graph. For each graph, there is a vertex set and the similarity matrix. Each similarity matrix characterizes the relationship between the sample pairs. For the intrinsic graph, the relationship measured by the similarity matrix is favored, and we try to preserve this kind of relationship in the dimensionality reduction. While for the penalty graph, the relationship measured by the similarity matrix is unfavored, and we try to avoid this kind of relationship in the dimensionality reduction. So for each similarity matrix S, its corresponding Laplacian matrix L is set as the difference between the matrix D and the similarity matrix, where the D is the diagonal matrix, and its diagonal element is the log sum of the similarity matrix. It's the traditional definition for the Laplacian matrix. Also, for the vertex, we assume that it is represented as xi, and its expected low-dimensional representation for the vertex is represented as yi. In the deduction of the graph embedding, we assume that the yi is of one dimension for ease of understanding, but I will introduce how to solve the problem when the yi is of multiple dimension. So a natural criteria to preserve the similarity matrix in the intrinsic graph is to minimize this object function. The yi is arbitrary and can be negative. For example, when the xij is large and positive, then it means that the two vertices are similar. Then the distance between yi and yj should be small in order to minimize the object function. On the other hand, if sij is negative and small, then we should maximize the difference between y and yj for the minimum. It means that the similarity between y and yj is small, then the similarity measured by the similarity matrix of the intrinsic graph is preserved. On the other hand, we try to avoid the relationship measured by the penalty graph, then we maximize the object function instead of minimize the object function. Then for these two objectives, we have the object function in the ratio form. For some algorithms, there is no penalty graph. So in this case, the B is a diagonal matrix and just used for the scale normalization. So the direct graph embedding directly computes the low-dimensional representation for the training vertices or training samples, but it can't be directly used to compute the low-dimensional representation for the testing data. To track this problem, we can extend the graph embedding into the linearization and the kernelization. For the linearization, it is straightforward. We assume that the low-dimensional representation of the vertex is obtained from a linear projection vector W. Then we have the object function for the linearization of the graph embedding. Notice in this case, the scale normalization on the low-dimensional representation Y is changed to the normalization on the projection vector W in the linearization of graph embedding. But a linear projection is limited and can't handle the case for the data with nonlinear structure. So a natural way to extend a linear algorithm into a nonlinear one is to use the kernel trick. Let the phi is the kernel mapping function from the original input space to another higher dimensional Hilbert space. As in most kernel-based algorithms, we assume that the projector function is a linear combination of the mappings from different training samples. Then based on the kernel mapping function K, we can have the object function for the kernelization of the graph embedding. Besides the extension of graph embedding in the mapping functions, we can also extend the graph embedding in the data representation. Tensor is a generalization of the concept of the vector and the matrix. Actually, vector is a first-order tensor, while the matrix is a second-order tensor. So in the algorithm, why should we represent objects as tensors instead of vectors? I think one reason is that sometimes the tensor is a natural representation for the objects, such as for image, it is a matrix and hence it's a second-order tensor. But for the videos or for the Gabor filtered images, they are in the format of the second-order tensor. On the other hand, the tensor-based representation has the potential to improve the learnability of the dimensionality reduction. For example, for 200 by 200 images, you extract the Gabor filtered images for 40, and if you consider it as a vector, and then the feature dimension will be about 400,000. But if you consider it as a third order tensor, and then the largest dimension from certain directions will be only 100. Before we introduce the tensorization of the graph embedding, I need to introduce the concept of mod K product of a tensor with a matrix. First, we review the product of two matrices. If the matrix Y is a product of the matrix X and U, then the column number of X should be the same as the row number of the matrix U, and each element of Y is the inner product of a row vector from X and a column vector from the matrix U. Now we take the model 2 product of a third order tensor and the projection matrix as example to introduce the definition of the mod K product. In this case, the projection, size from the second direction of the matrix should be the same as the column, a row number of the projection matrix. First, we unfold the tensor into a matrix along the second direction, and then we conduct the matrix-based production. Finally, we reorganize the computed matrix into a tensor, and in this case, the size along the second direction of the tensor should be the same as the column number of the projection matrix. Mathematically, the mod K product of tensor and the matrix is denoted as the times K. So, for the tensorization, we assume that each vertex is represented as a tensor xi, and its low-dimensional representation yi is computed from a series of mod K product with different projection matrix from different directions of a tensor. Then, based on this formulation, we have the object function for the tensorization of graph embedding. We can see that in this case we do not have closed form solution, but each time if we consider that there is only one projection vector unknown, then in this case is a linearization of graph embedding. Then we can obtain the solutions. So we can obtain the local optima by iteratively optimize the projection vectors. So we have the general formulation for dimensionality reduction. First, we have one intrinsic graph and a penalty graph. Then, if you try to direct compute the low-dimensional representation for the training samples of the vertices, then we have the direct graph embedding. We can have the linearization and kernelization if you try to conveniently compute the low-dimensional representation for the testing data. Also, for the tensor-based tensor data, you have the tensorization of graph embedding. So all of them constitute the framework of graph embedding along with its linearization, kernelization, and tensorization. So most previous algorithms for dimensionality reduction can be unified into this framework. Here I said most previous algorithms. I do not mean all the algorithms, such as the ICA and the CCA, and some algorithms cannot be unified in this framework, but most popular algorithms can be unified. This table demonstrates for each algorithm what is the intrinsic graph and what is the penalty graph, or what is the scale normalization matrix, and which type of graph embedding it belongs to. For example, for the PCA, its intrinsic graph connects to all the sample pairs with equal weights, and it uses the scale normalization to constrain the embedding, and it belongs to the it belongs to the linearization of the graph embedding. While for the LDA, its intrinsic graph connects the samples of the same class, while its penalty graph connects samples connect all the sample pairs with equal weights, and it also belongs to the linearization of the graph embedding. The details on how other algorithms can be unified into the framework of graph embedding can be found in the paper here. So I do not discuss the details here for the time limitation. So besides unifying most of previous algorithms for dimensionality into the framework of graph embedding and the extensions, it can also be used as a template to develop a new algorithm for dimensionality reduction. So if you try to develop a new algorithm, there are 3 steps. First is how to construct the intrinsic graph. There are many information can be used to construct this intrinsic graph. You can use the label information, class label information. You can use the geometry information such as these 2 samples are neighborhoods and these 2 samples are the marginal sample pairs from different classes. And you can this kind of information to construct the intrinsic graph. It means that you like to this kind of information to be preserved in the dimensionality reduction. On the other hand, if you want to get a solution, you need to constrain the embedding. As mentioned before, you can use the scale normalization. You can also get the constraint from a penalty graph. Finally, you just need to select which type of graph embedding you would like to select. There are 4 options for selection. Now I take the graph embedding as template to design a toy algorithm. This toy algorithm is motivated from certain limitation of the linear discriminant analysis algorithm. For the linear discriminant analysis of the LDA, it has the assumption that the sample of different class follow Gaussian distribution and with the same covalent matrix. But it is rarely to be satisfied in real applications. On the other hand, the available projection directions for the LDA is limited. So we try to design 2 graphs. One is the intrinsic graph, that is the interclass compactness graph. Another is a penalty graph, is the interclass separability graph. We use these 2 graphs to design new algorithm by throwing away any assumption on the data distribution. For the intrinsic graph, if one sample is a K1-ness neighbor of another one, and then we set this, then we connect these 2 vertices and set Sij as 1. For the penalty graph, if this vertex pair Ij is among the K2 shortest inhomogeneous pairs, means that if these 2 pairs are from 2 different classes, and then we set the Sijb as 1. Then based on these 2 graphs, intrinsic graph and the penalty graph, and from the framework of graph embedding, we can design different types of algorithms, such as for the linearization, kernelization, and the tensorization. For the linearization, this algorithm is called Marginal Fisher Analysis. It has the advantage of the original LDA in that, on one hand, there is no assumption on data distribution, hence it's more general. On the other hand, the interclass margin can better calculate the separability of 2 different classes than the interclass difference for the LDA. The toy example shows the results from the linearization of graph embedding, namely the marginal Fisher analysis and the LDA algorithm. The lines are the classification hyperplan for MFA and LDA respectively. We can see in this case the data does not follow the Gaussian distribution for each class. So we can see that the original LDA cannot find the optimal projection or the half-plane for classification, while MFA successfully finds the projection and the half-plane. We also use this toy algorithm for the face recognition problem by comparing with the original LDA. We tested 3 types of graph embedding, that is the linearization, kernelization, and tensorization. For the linearization algorithm, we conduct the PCA before the linearization. In this case, we conduct PCA to reduce the feature dimension into the sample number minus the subject number. We tested 2 types of experimental configuration, that is the G3P7 and G4P6. G3P7 means that we used 3 samples each subject for model training, while the other 7 images each subject are for testing. In this table, the data 2 here is the linearization of the graph embedding. And in the tensorization of the LDA and the MFA, we use the second order tensor, that is the matrices. From the results, we can see that the results from the MFA related algorithm are better than the results from the LDA based algorithm. But I think the most interesting observation is that in the case that we only have limited training samples for the model training, such as in these 4 experiments, their tensorization formulation can derive better results than the linearization and the tensorization. It shows the advantage of the tensorization in the case with a small number of training samples. But I think that for the tensorization, it's an advantage only in the case with limited training samples. If the training sample, anyway, tensorization is only a constraint, the linearization of graph embedding. If the training sample is enough, I think the linearization should be better than the tensorization. So I think these 2 types of extensions should have their advantage in different experiment setups. So let me have a brief summary on the graph embedding. So on the one hand, graph embedding along with its linearization, kernelization, and tensorization is a general framework that can unify most previous popular algorithms for dimensionality reduction. On the other hand, this framework can be used as a template for helping design new algorithms for dimensionality reduction. So let's begin. Let me introduce the second problem on the unified dimensionality reduction. That is, when the low-dimensional feature space is not a 1 dimension but a dimension larger than 1, how can we compute the how can we derive the optimal solution? In this case, here we focus on the case with linearization of graph embedding. But all the discussions here can be easily extended to the case with with other 3 types of graph embedding. For the multidimensional case, the constraint on the projection matrix W is very important. If you pose different constraints on the projection matrix W, then the result will be much different. So here, let the projection matrix denoted as W. Then, on the one hand, we try to preserve the relationship measured by the by the intrinsic graph, so we minimize the object function in this form. But because the projection matrix is of multiple dimension, so it is not a value, but it is a trace value of this matrix. On the other hand, we try to avoid the relationship measured by the penalty graph. Then we maximize the object function in this form. Also, finally, we are in the form of trace value. A natural way to constrain the projection matrix W is to require that the column vector is normalized and all the column vectors are linear independent. Also, you can also pose the constraints to require that the projection matrix is columnly orthogonal here. So for these two objectives, a natural object function will be in the trace ratio form. But unfortunately, there is no closed form solution. So in literature, this problem is transformed into the ratio trace form or the determinant ratio form. These two formulations can be easily solved by the generalized eigenvalue decomposition method. But which formulation should be more elegant? I think one criteria could be whether the object function has explicit semantics. Obviously, the trace ratio formulation has explicit semantics. For example, for its instance, LDA, its numerator categorizes the intra-class difference, while the denominator categorizes the intra-class difference. But for the ratio trace-based formulation, no such kind of explicit semantics exist. So another criteria I think could be whether the object function or the formulation is suitable for the consequent classification. For the ratio trace-based formulation, the object function is invariant to any four-rank transformation. It means that if you product another four-rank matrix into the projection matrix, the value of the object function will not change, but it will change the Euclidean distance measured in the low-dimensional feature space. And consequently, it will affect the final classification. But for the trace ratio formulation, it is only invariant to the orthogonal matrix. It won't affect the consequent Euclidean distance measurement. So from these two criteria, I think the trace ratio value formulation should be better than the ratio trace formulation for the dimensionality reduction. Then how can we solve the trace ratio problem? To avoid the singular value of the denominator of the object function, we transform the object function into another format where the SL is replaced by the ST matrix, where the ST is a sum of the SP and the SL. We also pose the constraint to require that the projection matrix should be columnly orthogonal. But this problem is still non-convex and we can't get the closed form solution. So we present an iterative solution to this problem, but we will prove that the iterative solution will converge to the global optimality. First, we remove the null space of the ST matrix in the object function because the null space of the LT will not affect the object function. We can come back to this slide because ST has included the SP, and both SP and ST are positive semi-definite. So it means that the null space of the ST will not affect the value of the object function of the trace ratio form. We assume that the SVD of the ST is U lambda U transpose, and the diagonal matrix and the matrix lambda only have the positive diagonal element, then we can constrain that the projection matrix is in the space spanned by the column vector of the matrix U, and we set W equals to UV, and consequently we can also transform the formulation in the case with the matrix V as variable. Note in this case, the new matrix in the denominator STU is positive definite. So we present iterative procedure to solve this problem. First, we initialize the projection matrix with 0 as arbitrary column orthogonal matrix. Then the procedure iterates between these three steps. First, we compute the trace ratio value based on the projection matrix from previous step, and then we solve a trace difference problem. The matrix is when we try to solve the trace difference problem, the matrix is a weighted difference between the matrix SPU and STU, and the weight is the trace ratio value computed from the projection matrix from previous step. It is a general eigenvalue decomposition problem, so we can easily obtain the solution. The third step is to reshape the projection matrix projection matrix Vm according to the eigenvalue of the STV. This step is of no use for the final solution, but it is useful for the proof of the global optimality of the solution. We can see that the original trace ratio problem is transformed into a series of trace difference problem. One does not have the closed form solution, but another has closed form solution. So let me introduce how to prove the global optimality of the solution. First, we prove that the object function will increase monotonically. Let the function Gn V with variable V is a trace difference value. Then from the definition of the trace ratio value lambda n, we can see that the Gn Vn minus 1 will equal to 0. But from the iterative procedure, we can have that Gn Vn will have the largest value for all the possible values of the Gn Vn. That means that the Gn Vn will not less than the Gn Vn minus 1. It means that the Gn Vn will be not less than 0. So we have this inequality. Because this matrix STU is positive definite, so we can have that the new trace ratio value from the current step will not less than the trace ratio value from the previous step. So it means that the object function will increase monotonically. Also, from the theory of point to set theory, we can have the theory 2. Because the proof is a little long, so I'm omit here just to give the final theory, final conclusion. For the iterative procedure, we can have the conclusion that the difference between the projection matrix of the successive steps will converge to 0. If the Vn converge to V, then we can have the conclusion that V will among the set for the projection matrix with the largest trace ratio value. It means that the maximum of the object function. It means that the trace ratio value will monotonically increase and converge to the global optimum. The details of the proof can be seen in this paper. It is the CVPR 07 paper. So besides the theoretical guarantee of the algorithm convergence, we found in our experiments that our procedure will converge very fast. Another researcher, Gore, also proposed algorithm to solve the trace ratio value, but the algorithm converges very slow, and the algorithm cannot guarantee that the object function will decrease monotonically. From the experiments, we can see that our algorithm, our procedure will converge after about 5 iterations. On the other hand, the trace difference value in this slides can well categorize the similarity between the projection matrix and the global optimum. From this figure, we can see that our procedure is much better than Gore's method, and we can see that the difference is of several magnitudes. We also tried our procedure on the LDA and the MFA. MFA means that the algorithm I proposed, Marginal Fisher Analysis algorithm. 3 databases are used. That is the Ferret, ORL, and the SimuPy databases. We also tried different experimental configurations. There are four categories of comparison. One is the RLDA. RLDA means that we conduct the PCA before the LDA and reduce the dimension to the sample number minus subject number. And the LDA is based on the ratio trace form. And the ITR means that the trace ratio based LDA. And also we have the other 3 categories. For the RLDA2 means that we first project the future dimension into a PCA space of sample number minus 1. From all results, we can see that mostly the trace ratio formulation will derive better results than the ratio trace formulation, but we have 2 exceptions here. So we can claim that mostly the trace ratio value will be better than the ratio traced formulation. So I have introduced 2 parts of the unified dimensionality reduction. That is the graph embedding, a general framework graph embedding along with its extensions. Another is how to derive the optimal solution for the trace ratio based formulation. It is a general solution for dimensionality reduction. Now I would like to introduce one of my latest work on how to rearrange the structure of a tensor to improve the tensor-based subspace learning. This work is motivated from the contradiction. That is, the success of the tensor-based subspace learning greatly relies on the redundancy among the unfolded vector. Means that if you look from one direction of a tensor, then the elements along this direction should have much redundancy if you want to conduct dimensionality. But the truth is that this kind of correlation or redundancy is not so strong in real data. For example, for this tall data and this real data, if you look from the low vector from this direction or from this low vector, we can see the redundancy for the elements along certain direction is not so strong. So intuitively, if you rearrange the tensor structure, for example, for this toy data, if you this third order tensor is just rearranged from this tensor, you can see that after the element rearrangement, if you look from one direction and then the vectors are very similar, I mean that the the relationship, the correlation among these vectors are enhanced. It is also the case for the vector, for the image matrix. These images are rearranged from these images. We just, okay.
You're showing two second-order tensors. Is there a third dimension that we're not seeing? It's just a grayscale?
Yeah, grayscale, yeah.
But you rearranged it to another...
Yeah, just rearrange the position of different pixels.
Okay.
So it means that after the rearrangement, you can see that the vectors and the columns are very similar. So it means that if you try to conduct dimensionality reduction, it is possible. Otherwise, for these images, it's not so easy to conduct dimensionality reduction, or you try to complex the images. So I take the second order tensor as an example to introduce how to enhance the redundancy among the second order tensor by the element rearrangement, because it's a second order tensor, and it means that it's a matrix, so I call it the pixel arrangement operator. Means that the problem is that after the pixel arrangement, means that Xi is the original matrix, XIR is the matrix after the pixel arrangement. Means that after the pixel arrangement, the matrix should be best reconstructed by two projection matrices U and V. Means that the reconstruction capability is enhanced. So the problem is try to find two optimal projection matrices U and V, and another pixel arrangement operator R. In this definition, we assume that the column number of the U and the V are predefined. Of course, you can also consider the U and V as variable, but I think if you just try to minimize the objective function, and then the largest possible column number will be the best. So we predefined the column number of the matrix U and V. So if for tensor-based subspace learning, you can use the rearranged tensor as the input of the tensorization of the graph embedding, and then can consequently enhance the algorithm performance of the tensorization of graph embedding. So this problem, we come back here. For this problem, is again an optimization problem without closed form solution. So I designed an iterative solution to solve this problem. First, we also initialize the projection matrix U0, V0 as arbitrary columnar orthogonal matrix. Then the procedure iterates between these three sub-steps. The first step, we reconstructed the matrix based on the projection matrix UN minus 1 and Vn minus 1. And the matrix is a rearranged matrix from the previous step. Then we have the reconstructed matrix UN reconstruction. And then we optimize the pixel arrangement operator R and the projection matrix U and V respectively. So the pixel arrangement of the R is defined as here, that after the pixel arrangement, it should be similar to the reconstructed matrices as much as possible. I will introduce how to solve this problem in the next slides, but here we just ignore it. Here, if you try to find another projection matrix U and V, it is an instance of the linearization of graph embedding. So we can easily obtain the solution. It's just a local optimum, but we can guarantee that the objective function will decrease. So we optimize the U and V respectively. But we have a very good property is that the difference between the newly rearranged matrices and the reconstructed matrix from the previous step will not less than the reconstruction error of the newly rearrange the matrix with the projection matrix from the previous step, we can see we minimize in this step we minimize these two terms, but this term is larger than this term, and in this step we will refine the u and v, means that the object function in this slice will decrease monotonically. So we can have the local optimum for the object function. So then, how can we solve the problem for the pixel arrangement? We try to find a pixel arrangement operator R such that the rearranged matrix will be similar to the reconstructed matrices. Actually, this problem is a traditional S-mover distance. The center is the original. The center is the original, no R here, the original matrix, while the receiver is the reconstructed matrix. In the transformed problem definition here, the P and Q means that the pixel index in the matrix, and then the cost from the index P in the original matrix and the index Q in the reconstructed matrix is defined. This is the cost. It's defined as the difference square of all the training samples. Also, for the pixel arrangement, there should exist one-to-one correspondence between the original matrix and the reconstructed matrix. So we have the constraint that here R PQ means that the flow from the sender to the receiver. So then we can have the constraint that the flow into the pixel Q should be 1, and the flow out from the P should be 1. The pixel arrangement is essentially an integral programming problem, but if the problem is defined in this case, it will have its linear programming formulation will have integral solution. So we just need to solve a linear programming problem. But in our implementation, we are constrained that the rearrangement will be constrained within local neighborhood. Means that for this pixel, we will only consider the pixels around it to improve the speed of the optimization. But in theory, we can guarantee that this problem is finally reformulated as a linear programming problem. So we can use the linear programming technique to solve this problem. We tested this procedure in two cases. The first case used one projection matrix, while the second, in this case, the algorithm is called the 2DPCA. Actually, it's a paper from a researcher in PAMI. Another case is we used two projection matrices, and in this problem is called the GLRAM, means that the generalized lower rank approximation of the matrices is a paper published by Professor Jieping Ye in the ICML. It's a best paper of that conference, a best student paper of that conference. We test the procedure on two databases. From the results, we can see that both algorithms converge after about 20 iterations. Here are the rearranged matrices from the algorithm of the GRAM and on the CMU-Pi databases. The first row is the original matrices. The second row is from the second row to the fifth row are the results from the algorithm with the projection matrix in different with different column numbers. The column number is from the 2, 3, 4, 5 respectively. We can see that after the arrangement, the column number or the column vector and the row vector are much similar than in the original matrices. Also, in this figure, the results are the reconstructed images from different algorithms without and with pixel arrangement. The first row are the results from the original images, while the second row are from the 2D pixel without pixel arrangement. This without pixel arrangement. These are from the results of the 2D pixel with pixel arrangement. And here are from the algorithm of GLRAM. From the results, we can see the visualization of the reconstructed matrices is much better than the result from the algorithm without pixel arrangement. Here are the results from the CMU-Pi databases. We can have the same conclusion that the pixel arrangement can enhance the visualization of the reconstructed matrices. We can have many extensions of this procedure to solve different problems. For example, we can use this procedure as the pre-processing step of the tensorialization of graph embedding. Also, we explored on how to transform the supervised subspace learning into the case for pixel arrangement. But here we not present a result here. Maybe sometime later we can show some new results on these extensions. So here I would like to give a final conclusion. First, I present a general formulation for subspace for dimensionality reduction, that is graph embedding, along with its linearization, tensorization, and kernelization and tensorization. Second is we provide a general solution for dimensionality reduction. That is, we claim that the trace ratio formulation is better than ratio trace-based ratio formulation. Finally, we present a procedure to do the pixel arrangement for improving the tensor-based subspace learning. If you can't remember the details of my algorithm, I think you can just simply remember these three simple object functions for these three works. Okay, that's all. Thank you.
Actually, I have two questions. First, can you go back to the slide where you showed convergence of your trace ratio?
Okay. You mean the work on trace ratio?
Oh, yeah, trace ratio, the convergence curve.
Okay.
Because I saw some, because in your proof, you proved that in the T, the value should be always, the objective function should be always larger. Oh, okay.
Oh, sorry. Here is a difference of the successive projection, the projection matrix. Yeah, we have the curve for the object function value.
So how do you explain the G-training on the curves? Like sometimes the difference becomes larger.
I think the difference can, because we did not prove that the trace difference will decrease monotonically. We only prove that the trace ratio value will the trace ratio value will decrease monotonically. For example, here means that you can for the trace difference, I think trace ratio difference. We can go back to this.
Yeah, because it seems you proved that the
Yeah, you can. Yeah, you can see from here. Here is a trace ratio difference, right? Trace ratio difference. This is the object function. We proved that this object function will decrease monotonically, but from this conclusion, we cannot guarantee that this value will decrease monotonically. But we have the conclusion that if the lambda n converge to the global optimum, I mean the lambda n is the global optimum, and then the trace difference value should be 0.
So the second question, so is the reconstruction.
Okay.
So here it seems that the visual quality of your reconstruction is better than without doing that. So did you count how many bits you are adding to that encoding process?
Yeah, we compute. Actually, we have the curve on the base to solve the projection matrices and the low-dimensional representation, and the base to solve the pixel arrangement operator. But here I did not display the result here. Is that we did not find the effective method to compress the index. So actually, the number of the pixels rearranged is very large. Especially for example, for the matrix-based, I think there should be about 1,000. But we also tried the procedure on the case for the set order tensor. Then the number of the rearranged pixel is very huge. So currently we are trying to find some solution on how to compress the rearrangement matrix.
So essentially that means the improvements in visual quality is actually because you have more bits actually being encoded.
Yeah.
Additional benefits of doing this?
We can have the curve on the reconstruction error and the bits to save all the informations. From that curve, we can see that there is even you consider the storage of the pixel arrangement operator, then the reconstruction error without the compression ratio is still much better. Is still better, not much better for the case with pixel arrangement. Okay. We also try to use this procedure for the graphics data. Maybe if I have a chance to visit here again, I can show you more results. Or I can send you the results by email. Okay.
I got a basic question. So since the images are represented in 2D, how do you use a 3D tensor to do the arrangement?
Oh, here. I mean, for the image, I just it is a second order tensor.
Right.
But for video, it's a third order tensor. Also, for the Gabor filter, it means that for each image, you can filter the image with different Gabor filters, and then you can have a sequence of images, Gabor filtered image, and then in this case, the Gabor filtered image can be considered as a third order tensor. But I'm not sure which case we can have the fourth order. I think for text analysis, there's some n-gram representation. You can have the fourth or even higher order tensors. Yeah.